I'll talk to you today about the strength and toughness of Lattice Metamaterials. I'll start with a very short, about my own definition of Archaic Materials. Like if you ask 10 people, you're gonna get 10 different definitions. So this is just another one of them, all right? So typically, you want to give the structure, right? And you go from solid mechanics to structural mechanics, right? You test the material, you make sure it, you understand how it fits and everything, and then you can put it in a big structure. So, Archaic Materials was an effort of a paradigm shift of can we go the other way around? Can we use structural mechanics and topology before you go to solid mechanics, right? So basically, you invert this whole paradigm and you use, instead of a big structure, a microstructure, and now this is your material, right? Or the other way around, if you want to think about it, if you think in terms of material design, instead of going through composition like an alchemist, you use geometry, right? Of a material that you already know the behavior, or you hope you know the behavior of the base parent solid. Now, why would you do that? A few reasons. One, you can achieve better properties than monolithic materials. Two, because you want to engineer a material that has the exact same property that you want. You don't want more, you don't want less, you just want the exact, Young's multi-resource strength. It's much easier to do it with a microstructure like that rather than a new alloy, right? Say I'm going to start with a new alloy, it's going to give me that Young's modulus. The third one is naturally you can get properties, especially in wave propagation, that it's impossible to get from a one-phase material. And last one, the last reason would be because you want to understand better several complex biomaterials that are typically, most of them architected. Actually, they're much more architected than the ones that we make ourselves, right? Because the base material, they're hierarchical and architected, so you have all different length scales there involved. So people have been making many different types of architecture materials, 2D and 3D, periodic or not, and the very solid, right? There's many different groups of families. It can be an elastomer, it can be metals, ceramics, active review here. And the length scales to change, depending on how do you synthesize the materials, right? All the way from the nano to, some millimeters. All right, so this all sounds great. Why is not everyone looking at the materials? They look great, right? And the problem is this: with all this flexibility that you can get all these different properties, understanding the non-union mechanics and failure becomes very complex. All right, because now you have to involve all of that, the geometry and all the solid structural mechanics go into this to understand anything past linear elasticity is kind of complicated. Now, all right, these are natural and some certificated materials. In general, you can think of it as a multi-phase composite where every phase could be void or any other material, and you get more of those combinations. And the applications typically are lightweight structures, thermal shielding, shock shielding, energy absorption, biomedical implants, acoustic insulation, and recently some new batteries, like making electrodes for batteries. Now, before I get to start my talk, really quickly, a few of the things that I'm not going to be on the talk, but if anyone wants to discuss about them, we do some work on these areas. We recently started working on instabilities in collagen scaffolds used for tissue engineering and implants. We've done a lot of work in the past on high-speed dynamics and energy absorption of lightweight foams, wave propagation in lattices and random foams, and when you see band gaps where no waves are transmitted through the structure. We'll be working on a new class of nano architectures that use synthetic DNA as a building block. And lately we've been playing with these cellular fiber reinforced composites, where you now, the base members here, you have fibers going through a cellular architecture. So feel free to ask me anything about those things, but they're not going to be in this talk. The only thing that I'm going to mention about elastomeric and metallic materials is just a little background information so that we can compare it, because everything we're going to discuss today is all brittle. So at least we have an idea of what happens when you have elastomers or metals. So we're talking here about lattices and foams, right? So periodic or highly irregular stochastic lightweight materials. And what happens is when you have elastomers, you have different modes of instability. All right, and they could be microscopic, you have basically different wavelengths. They could be at the 1 unit cell or few unit cells, or a global long wavelength vacuum mode. So it always ends up in a plateau. The difference in the mode we show here, whether you have a limit load or a monotonically increasing response. Now, if you go to the metals ones, the metal will typically have a limit load. So you're gonna start linear elastic. At some point, you're gonna localize, typically with a band somewhere forming, and then you get the plateau. And you can change those microstructures, or you can increase the loading rate. What's gonna happen is you're gonna move this plateau up and down. You can change the density, but almost always you're gonna get the limit load going up and down, and then pressing the plateau. But of course, by modifying the microstructure, you can change the hardening here. You can be more abrupt or more flat, and it all depends on what you want to do. Are you designing an energy absorber, or what's the exact application? So this is what happens with elastomeric lattices and foams and the metallic ones. All right, so today we're gonna All right, so today we're gonna talk about 3 things: the strength of brittle lattices, their toughness, and then a way to identify, can we correlate microstructure to properties directly. All right. So we start with the strength. So we decided, again, we have worked a lot on both metals and polymeric ones, and we thought we wanted to understand basically how different 3D topologies, right, behave when the base polymer, the base material at every strat is a very, very brittle polymer. So to test a representative set of lattice topologies, we use those 3. You might identify them. This is called the Kelvin cell. It's a model for, it's an idealized model of foam structure. Comes from Lord Kelvin, that showed that back then thought that that was the tessellation that minimizes the surface area. We know now that that's not true by the Weber-Feynman form, and basically this is called the tubocarhedron, and this is the octet lattice. And their difference has to do with the node connectivity, which means how many struts do you have at every junction. And that is well known in cellular materials, that basically as you increase the node connectivity, you increase the rigidity of the structure, right? So we wanted to see how much stronger is this one, right? So we designed different lattices, and we 3D print them. The base material is a photopolymer that breaks at maybe 1% strength, so it's just very, very good. And then we test all 3, and you see the results, and we repeated those tests. So these are average values in a way. So one thing is expected: the Kelvin, which is bending dominated. That means that when you compress, most of the struts are under bending, while the other 2 are stretching dominated. So you have more compression, right, in the ligaments than bending. So what happens is that, and you see here the failure modes, you see that the Kelvin, as we expect, is much weaker than both the octahedron and the octet. But the other two lattices have almost the same strength. Now, just a reminder, we changed here the connectivity, right? We went from 4 to 8, from 8 to 12. Now, the common thing is that the more you increase the node connectivity, the stronger you get. So we saw that this here was not the case.
That's how can I interrupt you with you? So you apply sigma. So you are interpreting this as material response. What happens when you make these specimens larger and larger?
Right, we did that. So they look small here, and they are, but we did 5 and 6 and 7 to make sure that we always get the same answer.
You always get the same. It asymptotes.
Yeah. And typically the rule of thumb is go 10 by 10 by 10, and that was what we usually do, because things tend to converge when you have either periodic or not a huge variance in your microstructure.
Tend to converge for what? Because elasticity converges fast.
No. Fast elasticity.
Yeah, strength. We don't know how. So you're saying that 10 by 10 by 10, you saw convergence of strength.
Right. We did in this case. Yeah, I was a bit surprised too, but. All right, so here's the questions. We only have one important question is, why is the octahedron equal to strength with the octet? So we'll come back near the end of this topic. All right, in terms of failure patterns, diagonal in the Kelvin, very widespread in the octahedron, and a little bit of an offset diagonal starting from the boundary for the octet. All right, so then we thought, we've been making micromechanical models for backing and for plasticity for a while. So we thought we have also for brittle forms, and we were feeling really good that we're going to capture this for sure. So here's a beam modeling framework that we have used in the past, where you discretize all struts with certain formable beams. You use a failure criterion that takes into account how much axial load you have, how much bending, and here's why you need that. And people sometimes tend to forget that. The strength of the brittle material is different under tensile loads, right, than in flexion. It all has to do with the flows in the material, the distribution, and all of this. So in this case, for this photopolymer, and we tested that in the company, kind of agreed with our values more or less. We had a little bit of a size effect. But it was basically the flexural strength was almost 2 times more than the tensile strength. So what you do is you have your beams that can fail at that value. Very simple element division for the failure that we have seen that for these relative densities, we've used it before for foams with different boundary conditions and different gradient densities, and they have worked great. So we thought it's going to work immediately for those lattices too. It's exactly the same thing, just a little bit of a different material. And here is the results from the beam models and the experiments, and there are kind of a few range of experiments. And as you will see, in all of this, you're missing something, either the stiffness or the strength, or both by a certain value. Now, those results could be good or bad depending on how much you zoom in. If I plot them in a log scale and tell you, oh, here's an ASPE map, you will think that, oh, that model works amazingly well. But if you look here and you say you have a good model, the answer is no. You're missing something. So the question is, if you see the failure patterns, they look very similar to what we expected. The diagonal in the Kelvin, a very widespread in the octahedron, and this offset diagonal in the octet. So we knew that the beam models do something good, so they can capture the stress distribution, but they're missing some critical stress. And basically what they're missing is the node, the junctions, right? You design those things in 3D. If you do them the right way, there is some smoothness, some fillet around the node that if you don't model it with beam, you're gonna miss something. If you model it with a beam, you're still not gonna get a complex stress state or a stress concentration near the junction. So you're gonna miss that. So then we thought we need to go and see the difference between beams and solids. So we went back to the solid modeling with unit cells, and we said, okay, first of all, do we have the same stress distribution? More or less, it was the same. But then, how much is the maximum stress? Is it even close, one and the other? And we found for a few of them a very big difference between the maximum stress, and as you can see, it's always that big difference, always near the norm. So the Kevin had a huge difference. The Hydro was not that bad. The Octet also had a very big difference. Now, this difference, I think I'm not sure next, depends on the relative density, which makes it even worse, because if you design and print something with a different density, and I ask them to say, oh, did you find any difference with the solid? One person would say, no, I think it's exactly the same with the beam. The other person says, no, it's very different. So it depends on topology and density. Maybe too complicated. But we thought, okay, now we can use the solid model that has these stress concentrations, and things should work. They will not, at least not immediately. Let's see. So now we discretize all structures with solid elements. The computational cost goes way up. Here's the problem. The rest of it comes from the problem I'm just going to say now. Element deletion works great for the beams, because what happens when you have these very slender structures, you compress at some point the beam breaks even near the node. So element deletion just is a very quick to get that. Now that you have the solid, element deletion is really not a great way to do fracture, right? On the other hand, you don't have that many options. The computational cost is already skyrocketing, and what are you gonna do? Any traction separation, cohesive loss, anything like that will make it basically untrackable. You're not going to be able to solve it. So what we thought is this: we have the beam models that do everything right, other than capturing that stress concentration. So when we build the solid model, can we try to make the solid model in the element deletion work a little bit as the beam model? So what we do is this: we take the stresses in the solids and uncouple them into axial and bending, the same way that is very natural, of course, in the beam elements. And then we extract this gamma parameter, again from the unit cells. So now we know for every topology and any density, how much stretchable bending do you have in the internal nodes, right? If you go for any strut, how much of it has an axial force N and the bending moment N, and what's the ratio between the stresses that come from those things? And we put that into our failure criteria over here. So now the failure criteria says that the stress will fail once it reaches a parameter times the tensile strength of the base material. And the parameter is just a function of bending to stretching ratio that depends on the topology. And of course, the flexural to tensile strength of the base material. So visually, think about it, you compress, right? And you have combinations of axial and bending loads everywhere that you know from a very simple even unit cell calculation, other than the boundary, maybe struts that you can redo that. And then you have different flexural and tensile strength. You add all of that into the model, and you get this failure criterion that basically tells you here, you see different values is that when you're away from, when gamma is very big, you have a bending dominated structure. So this will converge to the flexural strength. When gamma is very small, it will converge to the tensile strength. Over here, basically, is where you have compressive stresses, and this will just not fail. I mean, the compressive stress is, this compressive strength is so much higher that you're not going to reach it. And over here, basically, the compression negates completely the tensile strength, and that's why you get this increased strength. All right, so we had all of this, and now we're feeling pretty good about it. So now we go back to the solid model. These are just extracted units. It's the full finite size domain. And now, as you can see, the solid model was able to capture all the experiments. And not only that, we even looked at exactly the mode of failure, where does it fail and how does it propagate, and we're very happy with seeing very close similarities between the failure patterns in experiments and models. So when we saw that, we were like, let's do more experiments. All right, because again, you just never know with those things. There are so many parameters that sometimes you might even get lucky. All right, so we did different densities for all of the lattices, and for the octet, because that one was the harder to get in the first place. They had the larger level of the B model. We thought, let's go also to much higher densities, and we were very happy with the results. So now that we knew that, now that we have the model, we thought, let's do the scaling with density. If you've read Gibson-Nasby, the theory will tell you that, if you have a stressing dominated, it should scale with 1. If you have a bending dominated, it should scale with 1.5. That's the power of density. Many people have reported values that do not agree with that, because it's way more complex, right, than those simple dimensional formulas. So here we wanted to compare what is the beam analysis gives you, where those dimensional and scaling laws come from. What does the solid give you, and what can we learn about this? So here you see the Kelvin, the Foucault-Capiton, and the octet. Now the octet is very close to 1.12 for the beam, 1.17 for the solid model. But this figure here also shows you the importance of not looking only at scaling laws, right? Those two results are very different. If you only look at the scaling law, you might say, well, I have the right scaling law. But you try to understand how much is your strength. Look at the errors here. They're huge. So that first coefficient that people typically tend to ignore, this is very important, right? If you're doing engineering, you want to give the strength to someone. You cannot tell them, well, it scales like that. They just want for a certain volume fraction. Just give me how much is the strength, right? Which one's stronger? So again, the difference with density is a cumulative effect of how much is the stresses at the junction, how does that affect the density, and the increase of the axial stresses. We always divide those lattices into stretching and bending dominated. People tend to forget that if you get a bending dominated structure like a foam or a Kelvin set, and you start increasing the density, right, the axial stresses will increase. So it's going to go from a highly strongly bending dominated, where you have 99% bending and 1% stressing, to 80-20 or 70-30, where now you cannot ignore the axial stresses anymore, all right, in your analysis. And all of that comes down to the scaling. And as you can see, even though those structures are considered much weaker, as you go to higher densities, they approach the same strength size. So as you start increasing, even the bending dominated will get stronger now. And you can say, well, can it get equally strong? Yes, because remember that the flexural strength, right, is almost double the tensile strength. So that helps them get there faster. All right, so the other disadvantages have to do with asymmetry of tension compression. This is all compression, but if you start pulling, then those lattices behave in a different way. I don't have that here. All right, so that's all I have to say, I think, about strength.
Can I ask you before you move on to propagation? So if I understood correctly, you're saying that the problem is the junctions. Everything breaks at the junctions, is that right?
Right.
So
one problem is the junctions.
Sure.
The problem is the beams, right?
Sure, but it's breaking at the junction.
It's very complicated, right? Because it's not, in some of them, it would be directly at the junction, like breaking the junction. Some of them would be right outside, which means if it's right outside the junction, the beam can capture that.
But then, so here's the question. So you have your 3D model, right? You can look at the entire stress. You show some contours actually of the stresses, I believe, right?
Right.
They are fully triaxial. Why are you focusing on tensile strength when, in fact, the solid is not under any axial tension? It's in fact under it's the triaxial state of stress, right? So I'm a little bit surprised that you are only referring to two scalar values.
Yeah.
Right. So maybe how about shear? How about shear strength? Somewhere else.
That is a good point. The answer is we didn't know beforehand. What I mean is that I was hoping it would not come down to that because we didn't want to characterize the material this year and have to do all of this. Now, what we found is that.
But you're saying that for this material, but if I change my material and I look at the same geometry and I choose a material that is very weak in shear, then
it could play a role, but it could play a role in certain topologies, not in all of them. Because again, the junction can have some type of stress concentration, but that does not mean that the failure is going to be there. Right. It's a very delicate thing, right? Because the thing is, are you breaking the junction or it's going to propagate near the, where it gets a bit thinner, and then it's fine if you do that. So it depends on the topology and the base material. Right. Now, if we did all of this, what we did now, right, and it didn't work, then you have to go to full 3D fraction and do the shear, right, and do something about you need a more elaborate model for sure, and to capture it. I was very happy that we didn't have to do it, and we only had tension embedding, and it all worked there. But I wouldn't say that it would work for any material and any, it's all right. Now, strength is not easy to get it, but it's at least straightforward and everyone agrees. Fraction mechanics and toughness is a little bit more controversial. All right, here's a few key background information on fraction mechanics. So it always starts with Gibson and Asby, right? They were trying to understand brittle honeycombs and what is your toughness. And basically what they did is classical linear elastic fraction mechanics. And that has propagated for a while. So most of these works, and I'll talk a little bit about the two exceptions. What they do is you introduce a crack, right? And you apply some far boundary conditions, a K-field that comes from linear elasticity, and then you calculate your fracture toughness. You calculate KIC. Now, the only two exceptions is by Rifkin and co-workers that do a numerical local type of failure and propagation. It's really nice. And this work that has gotten kind of a bad rep, only because there is like some wrong scaling somewhere there. But the strength field theory is one would argue that would be the most reasonable thing to use here, because you obviously have different length scales in play. So again, in all of those problems here, you assume something, you borrow something from linear elasticity, all right? Whether it is for an orthotropic material or for an isotropic material, you assume that if you have a very long crack and somewhat infinite domain, those things should be okay. So the question is, for us, what happens if you don't think that that's the stress field ahead of the crack? Whether because your lattice is more exotic, it's maybe not stress dominated, or maybe because you just don't have infinite cells and a very, very long crack, right? And you can think about the specimens that we had before. What if you have 20 cells, right? Is that still a material? Can you have definition of toughness there? So it's a very, both theoretical and philosophical, but also a very applied question. So we thought, can we measure toughness by not having anything about stress and displacement? I don't want to borrow anything from elasticity, and I still want to say something about resistance to fracture of these lattices. And the way to do it is go energy, right? Ignore all these developments and go back 100 years to Griffith and say, well, I'm just gonna use Griffith criterion and the balance between surface energy and elastic energy, right? And use that to solve my problem. Now, the great thing about this is that, again, you don't have to assume you know, or you can predict the stress field ahead of the crack. The catch is, though, you need to know the orientation and the propagation of the crack, all right? Because you take these derivatives with cracking, so you really have to do that first. So the framework I'm presenting has 4 steps. Now, one is identify the crack path that sometimes might not be what you expect from classical monolithic solid mechanics. Calculate the energy release rate. We'll see how we do that. Measure the fracture energy from experiments, and then use the criterion to estimate the critical crack length or the critical microscopic stress, and then combine all of them together. So that's what we're going to do now, and I'm going to do it for two lattices: a very stretching dominated, the triangular lattice, and then the honeycomb, and we'll see the differences and what we can learn from those two kind of extreme cases. People think those are very average, but the triangular lattice is the highly stretching dominated. The honeycomb is highly bending dominated. So we'll see what happens in between. So the first is we need to understand what would the crack look like in a triangular lattice. All right. So we do a very simple analysis of a unit cell under tension and trying to understand what are the struts with the higher stresses, the most probable to fail first. So then we identify those. It's very easy. It's the group A here. And then we run a simulation where we remove one of those struts, right, in an infinite domain. And we say, okay, let's pull. And every time we remove, once you reach some type of stress, we remove one strut. Let's see how that's going to look like. And what you see basically is that the triangular lattice will behave as you would expect. It's going to grow horizontally. So now that we do have kind of a path orientation and propagation, we want to find now the energy release rate, and we're going to start with the crack profile. So again, we cannot assume when Griffith did that, he used the crack profile from the English solution, a paper of 1913, right, on notches in thin plates. We don't want to do that, so we go back to finite elements, and what we do is we simulate the crack, it's opening, and we use these nodal displacements, and we use this splitting function, right, with two geometric parameters, C and K here, and try to see how we can get that to work for all different geometries and crack lengths and everything like that. And as you can see here, the power law, it's always going to be very close to 1/2, no matter what the ratio of crack length to width of the plate will be. But the coefficient in the beginning, that in linear elasticity, this is 4. You see it starts from 4 when the crack is very small compared to the domain. But as you start increasing, right, you get a different value there. So now we have this fitting function for the crack profile. And then we're going to use the crack closure integral to basically calculate the change of elastic energy. It's a very easy thing to do. Here, gamma is a gamma function, and you end up with a nice closed formula expression, G. And you can even calculate it numerically and make sure that this formula works for all.
I'm sorry.
No, go ahead. That's why we're here.
Yeah. All right. I'm trying to understand. So I'm thinking about the things you did before. All right. One stress. In fact, you could argue that in lattice there is no toughness. All there is strength, because there is no. If I'm looking locally, you have a geometry that has no singularity, and it's going to break because some, let's say, tensile strength or whatever is going to be rich. And that thing is going to be, little thingy is going to break. Okay. If you were to use the model that you presented before to model this system where you can take strata, what would you get? That's one question. And why don't you use that?
I promise to answer everything.
Okay.
Well, not satisfactorily, but
okay.
I'll give you one type of answer.
Right.
Let me move on. But
yeah, of course. But essentially, I'm asking you. I guess you're going to link this back to the other thing.
I'm great. We get philosophical, but in a few slides, we'll go back to is this toughness? Did we measure it? Is that it? Is that? We'll go back to that. All right. Don't worry about it. So we have now again elastic energy release rate. If we have that, we want to compare some critical value, right, of that with fracture energy. How do we do that? We borrowed it from Ridley and Thomas that basically have these 3 different types of apparatus: a central crack, and an edge crack, and this opening tearing piece, right? Where you basically have specimens with different crack lengths, right? And at some point the work converges and you get the derivative, and that is your critical fracture energy. And actually, Yen and Thomas, a few years later, used it for rigid open cell phones. So we thought maybe it will work. Maybe that's how we're gonna measure our fracture energy. And you see here designs, right, of increasing crack length, and basically you see here how it propagates and it breaks the specimen in the middle. I think this one was a little bit of a different. We did this before the other work, so it's a little bit different polymer, but still highly rated. You see here force displacement. You extract the work at the critical load, and then you find basically you feed those and you get the derivative in the end, and you find some value of fracture energy. And we found like what, almost 124 joules per meter squared. So we're happy with that, but again, not sure how it compares with other things. We come back to that. Now, along with this thing, you can also think of this. The fracture energy of your lattice, right, will depend on the fracture energy of the base material, right? You break the lattice, but to break the lattice, you need to break the strut. The strut has a parent solid that has a fracture energy. That fracture energy is connected to the elastic energy of the base material at that point, right? So, and we were not the first ones to think of that. Actually, Get and Thomas did a very similar analogy and the scaling. So we thought, let's compare, and this is a very crude type of analysis. How much is that compared to if we remove a ligament, right? The energy of a ligament, elastic energy, right before it breaks. So that's what we do here. And again, because it's stress dominated, we know sigma F and how much the surface increment. So we have an approximate critical energy release rate. Again, by just using a very simple calculation, but it's gonna be practical near the end. All right, so let's put them all together. So you have the energy-based balance, right? Again, this comes from the experiments. You have the closed formula there. If on the right-hand side you put your analytical formula, crude but very useful, you can have a closed form expression for the microscopic critical stress. And then we compare with finite elements and stress calculations from finite elements, and what you can see basically. And now because we're at 25% volume fraction, and that had to do with the experiment, that was the lowest relative density that we could print with enough cells to have a crack and some certain width. So you see here that all of them are very close to each other, and all of them kind of follow the same trend. And when you have that, then why do I need the energy base and not go with the stress base? And the answer is, again, all of this is for the triangular lattice. The triangular lattice is the one 2D lattice material that behaves very close to a solid as possible. So the question is, what happens about all the rest, right? How much can you extend that comparison? So going back to the honeycomb, we did the exact same thing. So I'm going to go now much faster. We start with the first difference. You remove one strut from the honeycomb and you pull. There's not going to be any horizontal crack. So already now the deviations from the classical approaches are different, because if I go here and because I want to do a K field analysis and introduce a horizontal crack, one would argue you're never going to see that crack, right? It's never going to exist. You can measure something, but that's not going to happen in the honeycomb. It's not a natural flow of the material. So now in this case, the crack is in an inclined slope, and people have seen this before, so we're not the first ones to write that down. It doesn't change much for us, right? Again, we don't care about the fields, we don't care about anything. We can just have a little bit of an opening and a sliding component. Again, we just need the profile. We get it from finite elements. We again test all the fitting parameters to make sure that it works versus simulations. And then we plug those in, again, the same crack closure integral. You just have a little bit of a more complex expression. Again, two different geometric parameters. You end up with the energy release rate exactly the same way as before. A little bit more elaborate, but not a big deal. And now you go and do experiments. And the first complication is that our crack did not go all the way up along the same line. Now, if it didn't go even start that way, we would have a big problem. However, every time we zoomed in, we saw that the first couple of struts were along the same orientation as we thought it would go. So the results are still good, but then it turns. Now, whether it turns because those are the limitations of what we could print the test. So if there is a boundary effect, or if after fracture, remember we removed one ligament, right? And you see the stress state. Just because one ligament has higher stress, if it has 3% higher stress, and the numerical model this 3% makes a difference, in a real experiment that will not always be the case, right? So you have all these variations, and they're going to come into play. So now what we measure is the fracture range for the honeycomb, and it's almost 1/3 the one of the triangular lattice, which does make sense, right? The bending dominated should be less tough than the stress dominated. So we were happy with that result. And then we did the same approximate simple analytical calculation. If you remove the elastic energy of one strut right before failure, and you think about the extension of the crack, how much approximate critical energy release do you get? And then we put all of this together again. And now, as you can see, deviations will start to happen, right? Your formula is much, much cruder. Well, in this case, the strength, the stress criterion, finite elements, and the fracture one are kind of close too. Now, many people have values of, fracture toughness, K, I, C. So the question is, how do we use, our toughness, this gamma? For us, the fracture energy is the toughness, right? How does it compare, and can we compare? The answer is probably we cannot, but we can define, even though we don't want to use anything from linear elasticity, we pick this formula for now, just to make sure that, like, as a sanity check, all right? So what we do is we plug in here either gamma from our experiments or GC from the analytical formula that we have, and see how does that compare to what people that use the K field, from Gibson Asby, Norman Fleck has a very famous paper on that. And what we see is basically that the scaling intensity is very similar between the two approaches, but we find very different coefficients. The answer is because, again, when you do the K field approach, you already have separated into mode 1 and mode 2. While in our case, we have one value, right? And that is the fracture energy. And we think that we look around at more natural form cracks. So you're going to have a very different coefficient. And if you plot that, in an enhancement plot, you see that our rigid Wrigley lattices are right here. Here the honeycomb. Here's the triangular lattice, and we thought that makes sense. One is very close to ceramic foams. One is much higher. It almost gets close to metal foams that are, bending dominated. So it kind of all makes sense. Back to your question, Oscar. So there are two families of people, right? When you ask about how do you do fracture in those lattice metamaterials, right? I think two extremes. One is the minute you fail, remove one strut, you don't have a continuum anymore. Stop doing anything continuum with fracture mechanics. It's not going to work. The other family is like, just have a little bit of a large crack, have a large domain, it should all be fine. It's like linear elastic fracture mechanics. We're a little bit in the middle where we think this. It's very difficult to generalize about all lattices and say, and that's the mistake that people sometimes do. That they look at the triangular, like, oh, but that's what I see in a 2D lattice. And like, yeah, but in a 2D lattice, that if you look at design parameters that we give in 2 slides, it's on the very right end. It's not an average lattice. And it's very difficult to say that that will happen for all lattices. Now, I believe that I don't like the infinite domains and infinite cracks and no cracks, because we just don't have any practical applications, right? And it's not just because of our 3D printers. We use those in sandwich structures, things like that. Even with manufactured foams, it's very easy to have 50 cells, in your structure. And 50 cells, you should say something that you should consider that as material instead of a structure. So I believe that there is a continuum there, all right? My disagreement is with linear elastic fracture mechanics. I believe that energy is a little bit more appropriate, and that fractional energy could be the way to go. Now, is it